Welcome everyone to this new seminar from the One Word ABC seminar series and approximate Bayesian computation. So today's speaker is Rafael Itzbiki. Is an assistant professor at University of São Carlos and in Brazil. And is interested in methodology, applications, and foundations of statistics and machine learning. So today's talk is about likelihood-free inference, but in a frequentist framework, constructing confidence sets with correct conditional coverage. So thanks so much, Rafael, for being with us today. And again, if you feel like asking questions during the talk, feel free to unmute. Otherwise, you can write in the chat. But Rafael, the floor is yours. It's yours.
All right. So thanks, Humberto, for the introduction, and thanks for inviting me to be here. So I'm going to talk about how to construct confidence sets that have the correct or are close to the correct conditional coverage in a likelihood-free inference setting. So this is joint work with David Zhao and then Lee for at Carnegie Mellon University, and Nick Dalmasso, who's currently at JP Morgan. Right, so this is the ABC series seminar, so I'm pretty sure most of you are familiar with this, but just to make sure everyone is on the same page, in a typical parametric statistical problem, you have parameters, which I'm denoting by theta, and you want to make inference about these parameters. So you want to at least try to constrain what are decent, reasonable values for these parameters. And then to do that, you observe data, which here I'm denoted by x, and what links the parameters to the data is the likelihood function. And most statistical inference techniques, they require you to know the likelihood function, or at least be able to evaluate the likelihood function up to a constant or something like that. You need to, it needs to be tractable in some way. So that's the case for Bayesian methods. That's the case for likelihood ratio tests, maximum likelihood estimation, and so on and so forth. But in practice, in many science applications, although you have a parametric model for your data, this model is very complicated because it's given by a Ford simulator. So you don't have access to a tractable expression for the likelihood function. What you have instead, you can think of as a code which takes data as input and outputs observable data sets that come from this complicated stochastic process. And you can call this function, let's say, as many times as you want. Of course, there are some time constraints as well, but that's a separate issue. But the thing is, we don't have access to this likelihood function, and the question is, once you observe the data, how can you constrain data? How can you make inference about data just having access to this forward simulator? So just one example is n-body simulation. So that's a way of simulating the universe. So there are parametric models for how the universe evolves, and you can, and these are stochastic processes, and you can write codes that generate universes using these different parameter values. And the question is, how can you make inference once you see the data in the real universe just using these forward simulators? Okay, so as Humberto mentioned, most of the solutions are Bayesian. So of course, the most common solution is ABC. So here are two papers, but of course there are hundreds of papers, and it's a pretty interesting field. And I'm not going to go over ABC because most seminars you've seen probably have been about ABC. And there's a second related approach, which is related to ABC as well, which is trying to estimate the posterior distribution directly by using the fact that if you get draws from the forward simulator, so if you draw theta from the prior and then x from the forward simulator, you get a joint distribution, and the posterior distribution is just the conditional distribution of theta given x, and then you can use non-parametric statistical methods that approximate conditional densities to approximate this posterior distribution. So most of the literature has focused on Bayesian inference, like using these techniques. But the question we want to deal with here is how can we construct valid frequentist inference? And I don't want to go into the Bayesian versus frequentist But the fact is that there are some scientists that want frequentist guarantees for their procedures, and so we developed some methods to do frequentist inference in this likelihood-free setting. More precisely, the question we want to address in this work: how can we create valid confidence sets? And by valid confidence sets, what I mean is that we want the probability that theta belongs to your region to be 1 minus alpha for every theta. So again, what's random here in a confidence set is, of course, the set itself. This probability is conditional on theta. So what's random here is, so this is integrating over the distribution of the data given theta, right? And we want this to be valid for every theta. And that hasn't really received a lot of focus on even on the frequentist literature about likelihood-free inference methods. So there are some papers about frequentist inference, but they don't focus on like getting valid confidence sets. And that can be a challenge, as I'm going to show here, okay? All right, so our proposal to solve this problem is what we're calling LF2I. So I'm going to go over this in the next couple of slides. But just to mention, like to give a general overview of what I mean, of what's the approach, it's the following. So basically, we're going to use the forward simulator to do 3 different things. So there are 3 branches here in LF2I. So the first one is to, construct a test statistic. So let me just go one step back here. And again, we want to construct confidence sets. And the way we're going to do this is by inverting hypothesis tests. So we are going to use the standard Neyman construction of confidence sets by inverting hypothesis tests. So so let me discuss first how we are going to test hypotheses if we don't have access to the likelihood function. So the first thing we're going to do is to create test statistics to test this hypothesis. So I'm going to show 2 ways in which we can create test statistics, but there are other ways, okay? But having the test statistic is not enough if you want to test a hypothesis. You also need to be able to compute either critical values or p-values to know when you reject the hypothesis. So if you want to control type 1 error, and that's all you need if you want frequentist confidence sets here, you need to be able to estimate critical values or p-values, and that's what we're going to do in the left branch here. So again, we're going to use the simulator to estimate critical values or p-values. And then we're going to use the middle branch and the left branch to test hypotheses. And as I said, we're going to use a Neyman inversion to create the confidence sets. And then we have the final branch, which is the diagnostics branch, which is going to check whether the confidence sets really have the right conditional coverage. That is, whether this property is well approximated in some sense. Because, of course, the critical values are going to be estimated. So it might be the case that they are not well estimated, and we want to know that so that we can really make sure that we are doing the right inference, or if we should improve the critical values here, the estimate of the critical values. So there are these 3 branches, and that's what I'm going to go over in the next slides. Okay. All right, so the key insight to solve these 3 problems is to notice that the likelihood function, the critical values and the p-values, and also the coverage of the confidence sets, they are conditional distribution functions of theta. In a second, I'm going to tell exactly what I mean by that, but what this is going to imply from a practical perspective is that all these quantities, we are going to be able to estimate all these quantities using regression methods, standard regression methods. So random forests or boosting or neural networks, all of them can be estimated using such methods, okay? So, the setup we have is that we have data, which we assume we have n data points. This is the data that is going to be observed. We assume they are IID, and they come from a distribution f theta. I'm denoting a test statistic by lambda. So that's the test statistic we're going to use to test this precise hypothesis. So just one parenthesis here. In this talk, I'm just going to discuss precise hypothesis, simple hypothesis, theta equals theta 0. There are no nuisance parameters or anything like that here. In the paper, we also deal with nuisance parameters, but I'm going to omit for the sake of simplicity here. And so the test statistic, of course, is a function of the data, and it's also a function of the null hypothesis you are testing. So this is the theta 0 here. And we're going to reject the null hypothesis if and only if the test statistic is smaller than a constant. That constant, of course, is going to depend on the probability of type 1 error we want to make, and theta 0, the null hypothesis. So the cutoff can be different for different null hypotheses. Okay, and of course, again, the issue is how we create a meaningful test statistic in this likelihood-free inference problems, and how we compute cutoffs if we don't know the distribution. We don't even know that, if we don't know the distribution of the test statistic, how can we compute these cutoffs? Okay, so how do we create a test statistic? So there are many ways of doing that, and we are going to show one way of doing that. I'm not claiming it's better than the other ones. Of course, it's not better for all problems, but it has some advantages that I'm going to discuss. And in the last slide, I'm going to discuss other approaches that could be taken for this step. Okay. Oh, so one more thing I forgot to mention about our approach is that it's modular, in the sense that if you have a different way of computing a test, of creating a test statistic, you can still use the left and the right branch from our framework to your test statistic. And the same goes with the other one. So it's completely modular. It's agnostic to how the other branches were made. Okay. So, okay, I'm going to show one way in which we can create a test statistic. And the way that we create a test statistic builds on what's called the ratio trick. So that's an old trick in statistics to compute ratio of two density functions. It's been used in many places. It's also been used in the LFI literature. So here are some examples of papers that use that. And I'm going to show the way in which we use this trick here. So we are going to start with a rep. So we're going to use this trick to estimate the likelihood function. Okay, so first we're going to get an estimate of the likelihood function using this ratio trick. And once we get an estimate of the likelihood ratio function, the likelihood function, we are going to create test statistics based on that estimate of the likelihood function. So how does the trick go? It's like that. We start with a reference distribution, which is a distribution over the parameter space. If you have a prior distribution, it can be your prior distribution. Then we also need a second element, which is a proposal distribution. And a proposal distribution is a distribution over the data space. There are some constraints on what this proposal needs to look like. Namely, it needs to dominate f theta, the distribution of the data for every theta. One particular choice that works is using the marginal distribution of f theta with respect to this reference distribution. So that's what we've used in the experiments, because it naturally dominates f theta. Okay, so we have f theta, or we have pi theta, reference distribution, and proposal distribution gx. And now we are going to use the forward simulator in a particular way, which is a bit different from what we do in ABC. So we are going to create a data set, which I'm calling T, as follows. So first, similar to ABC, we generate theta from the reference distribution. Okay, so that's theta I. Then we generate yi. Yi is going to be a Bernoulli random variable, 1 or 0, with probability half. So it's a coin flip. Now, if it's 1, then we generate x from the forward simulator using theta as an input. But if it's 0, we don't use theta to generate x. We use g to generate x. Okay, so y is basically telling us whether x comes from the distribution given x, given theta, this particular theta, or from the proposal distribution. So that's our data set that we create using the forward simulator. So sometimes we use theta, sometimes we don't use it. Now, if it turns out that if you compute the odds of y, and this is what I mean by odds of y, so that's the probability that it's 0 divided by the probability that it's 0, probability that it's 1 divided by the probability that it's 0 given x and theta. You can apply Bayes' theorem here, and you're going to realize that this is just the density of this data point x under the model, right? Divided by the density under the proposal distribution of x. So the ratio of these two probabilities, the probabilities induced by this data generating process, is the ratio of these two densities. And what's interesting about this ratio of these two densities is that it's just one version of the likelihood function. This is a version of the likelihood function. So we usually think of the likelihood function in the continuous case as a density with respect to the Lebesgue measure, which is on the numerator. but it can be defined with respect to any other measure. So this is really the density. I'm writing in a simple way, but this is just the density of X with respect, the density of F theta with respect to G. Okay, the proposal distribution. It's a version of the likelihood function. This is constant in theta. So if you multiply this by the prior, you get the posterior. If you maximize this, you get the maximum likelihood estimator, so on and so forth. So this is really, this ratio of these two probabilities is the likelihood function. And what's interesting about that is that we can use probabilistic classifiers like a logistic regression or a neural network or boosting or random forest to estimate these probabilities using this data set. So in practice, what we do to estimate the odds, these odds, which is the likelihood function, is generate this data set and then estimate the probability of y given x and theta. So we plug them in here, and then you get an estimate of the odds. And once you have an estimate of the odds, you can define different test statistics. So we work with two test statistics in this paper. The first one is what we call the ACOR, and that is the likelihood ratio test. You get the maximum over the null of your test statistic divided by the maximum over the whole space of the test of the likelihood function. Sorry. So this is really the likelihood ratio test. But of course, we don't have the odds, so we are going to plug the estimates of the odds on this equation here. So we are going to get an estimate of the likelihood ratio statistic, and we also use what we are calling BFF, which stands for Bayesian frequentist factor, because it's the base factor, but we're going to use it with a frequentist goal later, which replaces maximization by integration. Okay. All right. So these are the two test statistics we are going to use. And again, I'm not saying these are the best test statistics, and I'm also not saying that this is the best way of estimating likelihood functions. But there are ways of, that's just one practical way of doing that. All right, so we have some theoretical results. I won't go into the details, but basically the first result is saying that we have Fisher consistency, which just means that if the odds is well estimated, if O hat is O, then we recover the likelihood ratio test and we recover the base factor. But we also have like some other interesting results about how far, so this is how far the power function of the test based on the estimated base factor is from the power function of the test that uses the true base factor. And what this result is showing is that they are close to each other as long as the number of simulations, which is B, is large. That's basically it. And there are other constants here, like kappa, which are related to the smoothness of the probability of this probability function here. Okay, so if this is smooth, basically what you can show, and you have a large simulated training set, what you can show here is that the power of the test we get using the estimated BFF is going to be close to the power you get with the true base factor. Okay. All right, so this is the middle branch of LF2I, and as I said, you can replace it with other test statistics, other ways of computing test statistics. So basically, we use a classification, we create an artificial classification problem to create our test statistics. Okay, now let's go to the second step. Let's assume we have a test statistic, which is lambda. Now what we need is to find the critical values. So I'm only going to discuss critical values here. In the paper, we also discuss p-values, how we can estimate p-values. So what we need is to find these cutoffs, which depend on theta 0 and of course alpha, in which you're going to reject the null if and only if the test statistic is smaller than this cutoff. Okay, so there are some natural ways of doing that, which is what people have been doing in the LFI literature. The first one is using Monte Carlo simulations, right? That's very natural to do. So you have your null hypothesis, you can simulate many data points at your null hypothesis using the forward simulator. And then what you can do is, you simulate many data sets under the null, you compute the test statistic for each of these data sets, and then you just compute the alpha quantile of this distribution. The distribution of the, so that's really one natural way of estimating these cutoffs. But the issue is that this is not practical if you want to do confidence sets. So if you are only interested in a single null hypothesis, that's a really good thing to do. But if you want to invert hypothesis tests to get confidence sets, that's not doable, because you need to do like expensive Monte Carlo simulation, or you do many Monte Carlo simulations for every single theta zero of interest, or for every single theta zero of the parameter space. Or it is like you need to grid the parameter space and then like do many Monte Carlo samples at each theta zero. So that's not practical if you really have this problem of, if you really want to construct confidence sets. So that wouldn't work. The second approach is to use some kind of approximation to the distribution of the test statistic under the null. So for instance, if we are using ACOR, which is basically the likelihood ratio test, we know that if the sample size is large and you have regularity conditions, then this is going to be approximately chi-squared. -2 log is going to be chi-squared. This has three main issues. First, the sample size may be small. Second, maybe the regularity conditions don't hold for this particular model you are working with. And third, the odds are estimated. The likelihood function is estimated. So we have no guarantees that it's well estimated. So we don't know if this is really going to be close to a chi-square distribution, even if the data set is large, if the true data set, the observed data set is large enough. So that might not hold this chi-square approximation. Okay, so it would solve the problem of estimating a cutoffs for all theta zeros at the same time, but it might not be a good solution if the odds are not well estimated, or you have the other issues I've mentioned. So what we propose instead is to use a quantile regression in the following way. So first we are going to generate, so we are going to use the simulator again, okay? So we are going to first generate from the simulator like we do in the ABC. So simulate data from the reference distribution, and then your data, each data point from the forward simulator using that data. So that's how we create this data set here. Then what we're going to do is to compute for each pair the test statistic. I just realized I changed the notation from lambda to tau here, sorry. So we're going to compute the test statistic that tests whether this data set comes from the parameter value that really generated the data set. Okay, so we're going to compute T1, T2, TB, one for each pair of data points. And now, like, the key insight is to realize that this cutoff is really the quantile regression, or quantile, yeah, it's the quantile regression of T given theta. So if you compute the alpha quantile regression, you estimate the alpha quantile of T given theta, that's exactly your cutoff at theta I. So what we do is to create this data set where you have theta 1 and then T1, theta 2, T2, theta B, TB, and apply a quantile regression method to estimate the alpha quantile as a function of theta. So by doing that, we don't need to have many simulations at each data point. In fact, this is amortized, like for any theta, even if it's not in this generated data set, you have a data that was not generated when creating this training data, you have an estimate of the quantile, of the alpha quantile. So you have an estimate of this cutoff. So by doing this, we get a cheap estimate of the cutoffs for all the parameter space at the same time. So this is really the advantage of this method.
Sorry if I interrupt you. So basically, you're computing these quantiles via regression for each pair. So you have B quantiles in the end.
It's more than B. It's really like we are estimating. So I can draw here. Maybe it's easier. I probably just need to share. Oh, I can. Okay, I can use select. Oh, okay. Okay. Let's see if it works. So let's think that we have a plot like this. We have like our parameter is real valued. We have our test statistic here. So for each point, like in this set, we have like what's theta and what's T, right?
Mm-hmm.
So I don't know, something like that. What we are doing is let's see if we can find another color. Estimating the alpha quantile of this data. Like it's really like it's a continuous function.
Mm.
So it's really we are estimating the probability. Okay, the quantile. Let's see how I can write this. The alpha quantile as a function of theta. Well, I mean, I don't know if you're familiar to these quantile regression methods, but instead of estimating the mean, like in regression, they estimate the quantile function, right? So although we have B points in this plot here, we are really estimating the quantile for the alpha quantile for every theta, because it's smoothing the curve basically.
Thanks.
Yeah, sure. Thanks for the question. So that's the main difference between this approach and Monte Carlo. In Monte Carlo, you need to fix theta. Each theta in principle, like it needs to be a fine grid over theta, because you're going to invert that to create the confidence sets. And then for each theta value, you're going to simulate many data points and then compute the alpha quantile of these data points. So, I mean, it would be very costly.
So since we are on the slides, there is a question actually by Pedro in the chat. I'm not sure if you just answered that, but he's asking, does each theta I generates a data set DI with how many samples?
Okay, so that's a good question. So DI has the same number of samples as your true data set has. So I'm denoting it by n here. So this is the observable, the data set that is going to be observed. It has n data points, and each D we're generating here really has the same number of data points. That's different from what you use in the first data set that was created. Here it's really X, like a single observation, because we estimate the likelihood function for that X, and then we multiply that to get the likelihood function for the whole sample, which is IID. So that's a good question. Yeah, that's something I didn't mention. D really has dimension n. No, it's not dimension, but it has n elements. Yeah, I hope this answers the question.
Okay.
All right. Let me just see how I can erase this. Okay. Oh, it's clear, better. Okay. So that's how we create critical values. And now like the final step of our LFI approach. So that's diagnostics. So once we have our region estimate, so basically we have our test statistic, which was the first branch. We have our cutoffs, which is the second branch, or the left branch. We invert the tests to obtain the confidence sets. Okay, so this is just the standard Neyman inversion. And again, what's nice about the way we are approaching this problem is that both quantities are amortized, right? So for any theta zero, you think about it's cheap to evaluate this cutoff once the quantile regression is estimated. And the same thing goes for the test statistic. Once you have the probabilistic classifier, you can evaluate the test statistic for any theta you're interested on. So this is really cheap to compute after you fit the probabilistic classifier and the quantile regressor. All right, but okay, the quantiles are estimated. So we want to know whether we have the right coverage. That is, we want to know whether this probability is close to 1 minus alpha for every theta zero. So what we do to evaluate this? We are going to use a similar trick to the one from the last slide, which is first we generate data from the fault simulator. Again, the I has n elements here, like in the previous slide. Then we compute for every pair whether the confidence set obtained using that data set, that particular data set, contains the value, the parameter value that was used to generate that data set. So basically, we're going to compute an indicator function, 1 or 0, for each pair here. Yes, it covered, or no, it didn't cover the true parameter value. So by the end of the day, you're going to have theta 1, Z1, theta 2, Z2, theta B, ZB. And what we do is just to regress Z on B, because the regression of Z on B, it's the expected value of this indicator function given theta, which is the probability that theta belongs to the confidence set given theta, which is exactly this quantity here. Okay, so the expected value of an indicator function is the probability that the event happens. And this probability conditional on theta is exactly what we want to be close to 1 minus alpha. So we regress the on theta. Again, it can be, you can use a logistic regression or a neural network or one classifier, one probabilistic classifier, and check if it's close to 1 minus alpha. And then you have some idea of whether you got the right validity, or if you need to improve the estimate of the cutoffs, or do something else. So this is really like a diagnostic branch. It's not just telling you if it worked or not, but it also gives you insights on how to improve. I'm going to show that in a second. All right, so let me show some experiments here. I selected a few of them. All right, so the first one is about estimating the critical value. So this is okay. So this is like I'm showing you the critical. So I'm creating confidence sets. They have nominal coverage 90%. So this is the black line. So across data, you want the confidence set to be close, to have coverage close to 90%. And let's start with this panel here. Here we are using our quantile regression approach, okay, to estimate the cutoffs. And what we see is that we have a coverage that is pretty close to 90%. So the method in this example is working well. There's only one parameter, one dimension, okay? Now what we do is to compare it to the Monte Carlo approach. So to make the comparison fair, what we do is to take the same number of data points that were used to compute the quantile regressor. I think it was like 10,000 here, and split those Monte Carlo samples in a fine grid over theta. So each bin is going to have very few data points, because we want the total number of data points to be 10,000, which is what we used here. And what we see is that, the Monte Carlo method is not working well. And that's because it's built using very few data points. It's not using them efficiently. That's the issue. It treats each problem separately. So if you have theta, 1 or theta 1.001, it's not going to smooth over theta to get an estimate of the quantiles. Yeah. And then we use a chi-square approximation, and it doesn't work at all. And the reason why it doesn't work is because the regularity conditions for this particular model we used for the experiment is not met. It's a mixture of Gaussians, I think, or something like that. So the regularity conditions used to prove that the likelihood ratio test has a chi-square distribution is not met in this example. That's why chi-square doesn't work at all. It undercovers. All right, so the next example is just to show some examples of confidence sets. Again, this is a setting where we know everything. It's just like Gaussian, so we know how to compute the true confidence sets we would get with the different methods. So the red is the true confidence set we would get with the likelihood ratio test, and the one with the base factor, inverting the test we obtain from the base factor. They are doing very similarly, and the estimated versions, which is orange and light blue, are close to the estimated ones, to the true ones. Okay, so this is just to show that the approach is going something that is kind of sensible. Now, another experiment which I think is more interesting is comparing the power curves of the different methods. And we're comparing the power curves as the dimension of the parameter space increases. So this is for 1 parameter, 2 parameters, 5, and 10. It's also a Gaussian example where we know everything, so we can compute the true A-core and BFF and get the true cutoffs and all of that. So for 1 dimension, if you have only 1 parameter, okay, so this is, forgot to say, we are testing the null hypothesis that theta is 0, and we're looking at the power curve as a function of where in the alternative hypothesis we are in, okay? And what this is showing is that for 1 and 2 dimensions, both like the true tests and the estimated tests do about the same. So it's easy to solve the problem when the dimension of the parameter space is small. But when you go to higher dimensions, things start to get much more complicated. So the estimated versions of the test statistics, that is the ones that use the estimated likelihood functions, they do pretty worse. So they lose a lot of power. And we do an analysis of the errors that are creating this loss in power in the paper. And what we find out is that there are 2 main reasons why that power is lost. The one is that estimating the likelihood function becomes harder, of course, when the dimension is higher. But there's a second reason which has a huge impact, which is that, well, ACOR has a maximization in it, and BFF has an integration. And we need to do that numerically, right? Because we don't have a closed expression for the likelihood function. It's an estimated function, so we need to do this numerically. And it turns out that either you spend a lot of time doing the numerical maximization or integration to compute the test statistics, or the power is small because they are not going to be well estimated. So it's not the test statistic. Well, the test statistic is harder to, the likelihood function is harder to estimate, but it's not only that, it's the integrating or maximizing the estimated likelihood function is hard numerically. So unless you put a lot of computational effort in doing this maximization or integration, you get small power because you don't maximize it well, or you don't integrate it well. So the conclusion here is that estimating a good test statistic can be hard in higher dimensions. Okay, and my last example here is about, so that's an application to high energy physics. So it's based on a real model for high energy physics. I won't get into the details about the model, but basically we want to detect some signal, and we have 3 parameters. So in this setting, there is one parameter you're really interested on, and we have 2 nuisance parameters. Okay, and so what we are using so these are the test statistics we are comparing, and we are using a version of ACOR and a version of BFF that handles nuisance parameters. So that's something I didn't discuss in the talk, but that we discussed in the paper. Okay, so let me go over the test statistics first. So we have 3 versions of ACOR. So this is the version that uses quantile regression. So we do ACOR in the way I showed you, but we use quantile regression to estimate, and we use quantile regression to estimate the cutoffs. This is a version where we use the same ACOR test statistic, but instead of computing cutoffs, we compute p-values. So there's a different way to compute p-values, and then we check whether the p-values are small or large to reject or not reject the null. And this is a third version, which uses the asymptotic distribution of ACOR, which is chi-square. So what's changing in these 3 versions is how we compute cutoffs, basically. So the test statistic is always the same. And then we have 2 versions of BFF. This is what I showed you using quantile regression to estimate the cutoffs, and this uses p-values. We don't have an asymptotic version of BFF because I don't think there's a nice expression for the distribution of the base factor under the null when n is large. Okay. So the first thing I'm showing is the coverage of the confidence sets we get by inverting the tests. The coverage is evaluated at a single point here of the parameter space we chose. Later, I'm going to show you how the coverage is across all parameter values. And the nominal coverage is 90%. So the first thing we see is that the asymptotic version of the test statistic overcovers by a huge amount. It was supposed to be 90, and it's like close to 97%. And maybe you can think that's okay. If it's overcovering, in a sense, it's worse. It's not. It's better than if it's undercovering, right? But when you look at the width of the confidence sets, so basically what we're doing here is to generate many data sets at that particular value where we evaluated the coverage, and plot what's the length of these confidence sets as a function of the dimension of how much it covers the parameter space. And what you can see is that for ACOR, using the asymptotic version, about 25% of the times your output is like the whole parameter space, so it's pretty useless. So it's overcovering, and it's overcovering in a really bad way because it's giving you the whole parameter space. The other test statistics are doing better in the sense that they get closer to 90%, and they are also giving more sensible intervals. So the length of the intervals are shorter. So that's that's good. So if I were to choose a test statistic here, I'll probably use BFF. All right. Now, what I think is the most interesting plot from the whole talk, it's this plot where we are applying our diagnostics technique, which is the regression of the coverage, which evaluates coverage for all parameter space. So this is the parameter space. These are the 3 parameters we have. And we're coloring the plots according to whether we have the right coverage, over coverage, or under coverage. So let's take the asymptotic version of ACOR as an example. So what we can see is that it's over covering the whole parameter space. So that's consistent with this finding at that particular value of the parameter space. So this is really happening all over the parameter space. It over covers. Now the other 2 plots, sometimes they have the right coverage, which is the green points here, and sometimes they under coverage, which is the red point. Okay, so green is the best of the worlds because that's what you want, the right coverage. Yellow is bad, but not so bad because it's over covering. So in the end, you're going to get wider confidence sets that you want, but at least you are not under covering. And the red dots is under coverage, which is pretty bad. So what's interesting about this plot first is that it's showing that choice here because it's not over covering the whole parameter space as ACOR, and more than that, it's under covering, which is the really bad thing, on a very small part of the parameter space, while ACOR is under covering on a larger part of the parameter space. So if I had to choose between these 3 methods, again, I would choose BFF, especially like if I think that my parameter value, my true parameter value lies in this region here. So if I think like, unless there's a really high probability, I think, in a Bayesian sense, that my parameter value is close to these edges, I would stick to BFF. So that's one thing, which is the insight we get by applying our diagnostics to these approaches. And the second thing, which is interesting, is that by looking at that, you can try to recalibrate the quantile regressor. So you can see that the main issue is happening here, and you can sample more data points here and then refit your quantile regression. So you can really augment that data set we use to train the model, to train the quantile regressor. You can augment it with more samples in regions where the coverage is not well estimated, and then recalibrate the cutoffs, and then you can even apply these diagnostics again to check if things improved or if you need to improve them even further. So this is really giving you insights on how to improve, and I really like these plots. Okay, so just to conclude here, so this work was mainly about validity, how to try to achieve validity in a frequentist sense, and more than that, how to evaluate whether it was achieved or not and how you can improve that. And I think this is really the first work that tries to address this directly. And the conclusions from the experiments I've showed, and also the other experiments we have in the paper, is that the hardest thing to achieve in this LFI frequency setting is power. So especially if you have many parameters, it's really hard to get high power. And I've discussed 2 reasons. One is that it's hard to estimate the likelihood function, and the second one is like a numerical integration or maximization problem. But the good thing is that there are some alternatives we can try to use, and they can be used within our work. So you can think of other ways of creating test statistics that maybe have higher power, and you can still use the left and the right branch of the LF2I approach. So quantile regression, and then diagnostics. And so here are some options. So first, you can think of better estimates of the likelihood function. So there are many ways of estimating likelihood functions. So for instance, Bramer has a way of estimating likelihood functions that can work better if you are in a setting where by augmenting the likelihood function with latent variables, you can evaluate that likelihood function. So you take advantage of that fact. So if your model has this property, like if you have missing data or something, then you can estimate the likelihood function in a more efficient way. So I think it's called mining gold or something. this paper by Humberto has a sequential version of how to estimate the likelihood function, which takes advantage of the fact that you're doing this sequentially to get a better estimate of it. And so there are other ways of estimating likelihood function that would solve some of the issues. Another direction which I think is interesting and we didn't explore in the paper is that BFF, because it's a base factor, you can use it with a meaningful prior information, if you have one about the problem, to get better power in the region where you think that the parameter lies on. Okay, so if you use a very informative prior information, typically what you're going to get is to get higher power in that region of the parameter space, which means shorter confidence sets in those regions. And so if you have a meaningful, at the expense, of course, of having wider intervals for other parameter values. But so if you have a meaningful prior, you can use it within BFF to get better power. And third, like that's another option we've been working on with Luca and Michael. So that's a different test statistic. It's based on the Wald test statistic, but it's a Bayesian version. So instead of using the maximum likelihood estimator as Wald test statistic would, we are using the posterior mean and the posterior variance on the denominator here. So what we do is to estimate this test statistic. Again, of course, we don't know the mean, and we don't know the posterior mean, and we don't know the posterior variance in an LFI setting, but we can estimate it using regression or using like random forest or any other regression method. So what we do is to estimate this test statistic and then use it as a test statistic to create a test and then invert to get confidence set. So in this way, we avoid having to estimate the likelihood function, which is complicated because it's a function of both x theta, and it's like a whole density function. So we're just targeting the posterior mean here and the posterior variance, which might be easier in some settings. And we are getting some interesting results for some problems. All right, so what I've showed you here is appeared in ICML 2020. Especially the part about ACOR was in ICML. And then we also have a new paper, which is on the archive, which has the other things I've showed you today, and also some more experiments. So again, thanks a lot for having me. It was really nice.
Thanks a lot, Rafael. So I upload, and I'm sure that everyone else is joining me. And I stop now the recording before we start the question and answer session.